Okay, so I'm going to cover a couple of topics, and they're sort of all related actually, because they're all to do with interferometers, either in the time domain, I think you could say, which is like Ramsey Spectroscopy. It's associated with sort of an interferometer path that happens as a function of time, or interferometers that happen in space. They're very, very similar. You can see that a lot of the mathematical relations are actually almost exactly the same. And so what I thought I would do here, this is actually not a PowerPoint presentation, this is a mathematical notebook. So I'm just going to work you through a little bit how the quantum limits of sensing come in interferometers, and show you how you can improve upon those by using delicately prepared quantum states. So the idea is that there are two kind of limits in interferometers that we talk about. One is called the standard quantum limit, and I'm going to show you that first, and the other is called the Heisenberg limit, which is kind of the ultimate limit that quantum mechanics allows, as far as I know anyway, that you could ever achieve. So this is the sort of premise. This is our basic interferometer that we've been talking about in a number of these lectures. So the idea is that you send in here some photons, for example, in a coherent beam of light, so maybe a laser, and the photons get split by a beam splitter along two paths and then recombined. And then we ask the question about what is the flux of photons? What is the likelihood of a photon coming out in either port 1 or port 2 of this second interferometer? So this is how all interferometers work. A Michelson interferometer is a folded version of this. Basically we have two paths. And what happens is, as we change the effective length of one of these paths relative to the other path, we can change whether constructed interference of the two amplitudes occurs in this port or in this port. And so as we change that, we can introduce here a phase shifter, which is like a delay. As we change that phase shift between 0 and 2 pi, what we see is that the photons would oscillate between going all to 1 and then all to 2 and all to 1 and all to 2 and so on, backwards and forwards. That's how it follows. So that's going to be our paradigm system. And I'm going to talk about basically four topics briefly here. So first of all is going to be the idea of how do we use interferometry, and how do we think about interferometry as a parameter estimation problem, which means that this is what we always want to do. We want to run our experiment, measure some photons, and then ask the question, what was the phi? Like, what was the phase shifter that was in the interferometer? I'm going to show you that if you do this with independent particles, so I use a laser well above threshold as described by coherent state, and use that in my interferometer, then we get a sort of a limit in interferometry, which is called the standard quantum limit. And this is always going to be our baseline. And in the quantum science, we're always wanting to improve upon this. And I'm going to show you probably the simplest example that goes beyond this, of a fancy quantum state in the interferometer, and that improves upon the standard quantum limit. And I'll just briefly show you what happens when you start to think about imperfections and how that gets degraded. So, so here is our interferometry. We've got the Mach Zehnder is going to be the thing we're going to study. And there are many other systems that we can map onto this. So I think I could think about this same idea with spin systems in a Ramsey pulse kind of sequence. And there are many other actually two-path systems, either in space or time, that have this topology. And the goal is going to be to measure phi. So let's set this up. So we're going to firstly construct a little function here, which is the probability of a photon to be detected in port 1. So this is a little function p, and as I said, it goes back and forward between the two ports in a cosine squared function. Okay, so it oscillates twice in 2 pi. And every time I throw a photon at an interferometer, I have to make a random choice based on that probability distribution. So the interferometer throws dice, and a given photon that I throw at an interferometer will either come out in 1 or 2, and I'll detect in one or the other. And which one it comes out is going to be dependent on my phase shift in the interferometer according to the cosine squared function. So we can simulate this. Let's do that. So we can make measurements. Here is the measurement, a simulation of an interferometer that has a pi/4 phase shift, a 90-degree phase shift in it. This photon came out in port 2. You can say, what information did that give me? I saw a click in port 2. What's the phase shift of the interferometer? And the answer is this tells you essentially nothing, right? It tells you very little about the interferometer at all. I could do it again and get a different result. Get the same result, get a different result. So individual photons always make a choice. The interferometer is throwing dice. It's playing random numbers. We could do this for 50 little dice. We could run 50 photons through my interferometer. They choose one by one to go through 1 or 2. I could do it again. I'm going to get a different result. And the question is, what is this result, which I will call the measurement record? That measurement record is what the experimenter writes in their logbook. They've got 1111121. Those are the results of a simulated interferometer experiment. And the problem is a problem of parameter estimation. You want to take that measurement record and say, what is the phase shift of the interferometer? What is the phi? In this case, the measurement result was 33 came out in port 1, 17 came out in port 2. So you can see it's just throwing a binomial, it's constructing a binomial distribution by throwing dart. And then you can get an idea of what the fringe really means. So here I've got a little simulation of that, which I'm doing for every little phase shift in the interferometer. Here we're doing the simulation every phi along here. And I'm going to change here the photon number. So for example, I've set it to be 1. What happens if I throw a single photon at an interferometer and try to do this parameter estimation for each phi? And then I can calculate the number that came out in port 1 divided by the total number of photons that went into the interferometer. And in this case, where I only have 1 photon, I either get a 1 or a 0. I get a 1 if it came out of port 1 and a 0 if it came out of port 2. And so I do that for every phi, and what I see is this distribution. And the question is, what is the phase shift in the interferometer? And you can look at that thing and tell me, it doesn't provide much information. But as we start to use more and more photons, we get a better and better idea. So as we go up to say 5 photons, you can see we can have, did I get 5? Get 5. We can have 0, 1, 2, 3, 4, or 5 that are different output results in the 2 different ports. And simulating this with that cosine square function, you can start to see a fringe build up. So what that fringe is just this combination of these kinds of experiments. And eventually, as we start to throw large numbers of photons, you'll start to build up the fringe that we think of when we think of interferometry. But really, this is what's going on. We really have, we're accumulating data about 1s and 2s, and we're constructing this. So there's intrinsic noise based on this, based on the fact that we're throwing a dice for every photon. Right? And as we build up more and more of these things, it looks smoother, but it never goes away. It slowly starts to coincide with the actual answer. Cosine squared of phi, if you remember, is the true probability distribution. And so it starts to match the true probability distribution, but we always have noise. And that's always fundamental to this problem. Okay, so all I'm doing is showing you a simulation of the extraction of a statistical result from a known probability distribution, which is that, we have a probability of coming out in 1 and 2, and that probability distribution is found by throwing dice multiple times. So the answer is going to be binomial distribution. And I can plot the binomial distribution for different numbers of photons as a function of phi. It looks exactly like what I was just simulating. So we have 3 things we can sort of think about. The true probability distribution of the interferometer. As I get fewer and fewer photons, the binomial distribution gets fatter, just like the simulation did. We can sample that distribution by running an experiment. Or we could ask, what is the statistical distribution that underlies that experiment? And that's the binomial distribution. So this is sort of implicit. This is part of the story of an interferometer. Okay, so all quantum measurements are going to look like this. So let's move on. So what is the precision to which I can determine delta phi by knowing that fringe? And what I've just been arguing is that there's always going to be a spread of the numbers, delta n1, based on the distribution of photons that come out. Well, you could sort of say that uncertainty in the number, based on the fact that I'm throwing dice, is the same as an uncertainty in the phase shift, which is the parameter that I'm trying to estimate. And the things that connect that is going to be the slope of this line. Okay? So the slope of the interferometer tells me about how I connect the intrinsic uncertainty, which is due to the shot noise, the quantum noise of individual photons taking the path that they do, compared to the slope of the interferometer. So what I can do is, I think I'm just going to do this here. So what we want to do is to infer, we've got an interferometer set up with a certain phase shift, and we run the experiment and we count how many photons come out in one arm, and we want to infer what is the value of the phase shift of the interferometer. That's what interferometers do, they measure path length differences. We have a noise, an intrinsic noise, delta N1, in one of the ports, N1. And as I just said, that translates to a noise in the parameter that I'm trying to estimate. The relationship involves the gradient of this plot above. So delta phi is d phi dn1 times delta n1. And this thing here is the gradient of the plot above, dn by d phi. We want the magnitude inverse here. It tells me about how those uncertainties are related. So we can actually derive this. So what I'm going to show you here is the fact that when you have a large number of photons, the binomial and Gaussian distributions start to look the same. And so you can combine the results using the central limit theorem. You get an simple algebraic answer for what the uncertainty in the phase shift is. So that would be the case of independent statistics when the central limit theorem is valid. So let's go through some of these things. First of all, let's talk about what this N1 is. So the signal and noise, the signal is how many photons come out in port 1. And that's just the number of photons that I throw at the interferometer times the probability that it comes out in port 1. So n times p of phi is the same as the distribution, the number of photons that on average come out in port 1. And that's the signal of my experiment. And then the uncertainty is related to the delta n1. And we can obtain that pretty easily. That's also straightforward for this simple example here. Here is the full answer. So what is the uncertainty of the number of photons in port 1? If I throw a single photon at the interferometer, well, the uncertainty is the root mean square. So it's the square root of expectation value of n1 squared minus expectation value of n1 squared. That's just the definition of delta n1. But if I only have a single photon, I only either get a 1 or a 0. And so the expectation value of n1 squared is 1 squared, which is also 1 times the probability of getting it. And the mean value is 1 times the probability of getting it. So the 1s or 1 squareds go away. And I just get the probability of phi minus the probability of phi squared. So that is the delta n1 for a single photon thrown at the interferometer. And now I can employ the central limit theorem and say I've got lots of these happening and they're all statistically independent. And I add them all up using Gaussian statistics. When I do that, I pull out a square root of n. So the uncertainty in n1 for n photons going in is just square root of n times larger from the central limit theorem. So it's the same formula, but with the square root of n out the front. And then all I have to do is to go back up to my formula and say, what does that tell me about the phase shift in the interferometer? Here it is. Delta phi was equal to the inverse of this derivative times delta n1. Delta n1 is given by here. The function is given here, and I can just differentiate it with respect to phi. So here I've asked Mathematics to go ahead and do that. Multiply n times p, that's the signal, find the inverse of that derivative, multiplied by this function that we just derived here, and it spits out this thing. 1 divided by 2 times the square root of the difference. That's called the standard quantum limit. As you throw more photons at the interferometer, the uncertainty, the phase resolution in your parameter estimation only goes down as the square root of the number. And that's it's called the standard quantum limit. It's not standard, it's not quantum, it's not a limit. So, but that's what it's called. Okay. Note that this is completely independent of phi. And that's something that's maybe not so obvious, actually. This result, the end result up here is that phi disappears altogether and only contains the number of photons. As you sort of move around on this interference pattern, you get big fluctuations in the middle where the gradient's big. And as you go up to the top, the fluctuations get smaller, but the gradient gets smaller. And the whole thing turns out to be a complete wash. And you can run the interferometer anywhere you like, and you always get the standard quantum limit. And I don't think that's obvious at all. That's something that's a derived result. That's something that comes out of this derivative. Okay, so any questions on this? This is classical lasers, driving interferometers, and what the limit is.
Yeah. So the result for the power expand is just -1 over 2 squared.
Well, the minus shouldn't really be there because I should have taken the absolute value of it. I just noticed it. Because it's the gradient.
So my question is, what's the answer? What's the result for?
Well, this is so delta phi is 1 over 2 root. Okay. So, parameter estimation. Okay, let's go a little step further and talk about what's really going on here. We are measuring photons and we're trying to infer the parameter of a system. In statistical physics, this is the Bayesian problem. Basically, you have a system that you know how it runs, you're measuring outputs, and you're trying to ask about what the parameters in that model was. The forward model, the model so the interferometer has a certain phase shift. I measure some outputs and I want to ask the question about what that phase shift was. So just to show you what the Bayesian theory looks like, basically you want to find the probability that the interferometer has a phase shift of phi, given that you've made a number of measurements of the output. You've thrown photons at it and you've detected them in the output points. So Bayes' theorem involves two effects, basically A or B. And it uses the fact that the conditional probability, the probability of getting a given B, is equal to the probability of A and B over the probability of B. That's the definition of a conditional probability. And it also works the other way around. The probability of B given A is obviously by symmetry the probability of A and B, or B and A, which is the same thing, over the probability of A. And so Bayes' theorem just says, I can make this numerator here the argument of both of these equations. I can set them to be equal because the probability of A and B is the same as the probability of B and A. They're exactly the same. And then I can construct a very simple expression which allows me to do parameter estimation. So just algebraically, when I combine these two things, I get the probability of A given B is equal to the probability of A times the probability of B given A over the probability of B. And these all have meaning in this problem. So this is just simple algebra, if you like. But let's apply it to our problem, and you'll see why it's useful. So we set A to be equal to the phase shift of the interferometer, B equal to the measurement result, which is the number of photons in port 1. So what Bayes' theorem tells us is that the probability that we want, the probability that the phase shift is phi, given that we've made a measurement of N1, is equal to what we call our prior knowledge, the probability of phi, before we went in and made the experiment, times the probability of seeing this result, N1 given phi. So given that we have phi, I can tell you how to solve the interferometer problem, and this is called the forward problem. This is like, what is the probability of making this measurement? And this thing on the bottom, the probability of N1, I don't need to worry about, because probability is always normalized to unity. So I don't have to calculate the bottom, I can just normalize my entire result for all possible phi's, and I'll end up with the correct denominator. So that comes for free. So these are all the things I know, the forward problem, the prior knowledge, and the thing that I actually want. And so this problem of parameter estimation is basically a problem of Bayesian analysis. And there are other ways of framing this, but I think this is a pretty simple way to do it. And I'll just mention one more thing, that you can iterate this formula. So if I have a new measurement, N1 and N2, I get some P primed of phi, just iterating this expression, times Pn1, N2 given phi over Pn2. This thing is the probability distribution for phi from the first measurement. So I can substitute that in using this result and so on. And I can keep on doing this for the third and fourth measurements. And you can see there's a pattern develops. You basically have the first prior times all these things on the numerator and all these things on the bottom with just N1, N2, N3, N4 and so on. So you can write this in this form where you've got the prior and the probabilities of all of these things. So as I make more and more measurements, Bayes' theorem tells me how to keep on combining the results and estimating parameters. And that's really at the heart of quantum metrology. This slide is very, very general to lots of measurement problems. And I'm sure it'll come up again in other talks. So here's a simple example. Let's say that we have an interferometer that has a real phase shift of pi14. So I put it in the box and then I close my eyes and I say I don't know what it is, and I'm trying to estimate that using simulation. So we have to start off with a prior knowledge. Well, I don't know, let's say that we know for sure that the interferometer phase is somewhere between 0 and 90 degrees. Okay? and it's actually 45 degrees, but we don't know that. So here's our prior. Our prior is completely flat. Somewhere between his unit norm, because it's a probability density distribution, it's between 0 and a pi halves, and we don't know anything more about the interferometer. That's called the prior. And then we can go ahead and we can simulate what happens if I throw photons at my interferometer. So I have a probability of getting a 1, which is this cosine squared function that we talked about at the beginning, and a probability of getting 2, a probability of getting 2, which is 1 minus that, so the sine squared function. And here's a piece of mathematical code which does what I'm talking about. It says that I can take a measurement simulation, just like I did before. This is the same thing we were using before to simulate 1s and 0s, and I can get a result of this by throwing dice. And then I can ask what happens if I take that and I apply a Bayes theorem, and a normalized version of Bayes theorem, where the normalization involves integrating the prior up and dividing by its integral between 0 and pi 1, 2. So this normalizes the probability distribution. So what we're doing here is we're taking our prior, we're multiplying by the probability that we'll get our result, and we're normalizing it. That's Bayes theorem. So this is just mathematical language for those equations that I've got. And you can simulate this guy then. You can just run ahead and do some simulations. You can trust me that there's no book runs, but I'll just run down here for the sake of brevity. Here I ran the experiment once, and it decided to come out in port 1. So I update the prior, and I find a new probability distribution called P1. I throw another photon at my experiment. It simulates, this time decided to come out in port 1 again. And so I get a new prior. And sometimes it'll be 2, and sometimes it'll be 1. And then down here I'll show you what the state of the probability distribution looks like as I start to accumulate data. So I started off with a flat prior like this, and then I got a 1 and it decided that that was the new probability distribution. And then I got another 1 and it decided that that was the probability distribution. So what happens will be the accumulation of all of these simulated events. And that is somehow the optimum way that you can reconstruct the probability distribution for that observable. So just to show you how this works, you can keep on cranking out new simulated results. So here is 30 of these guys, a 1 and then a 2 and then a 1 and a 2 and then 1 and then 1, 1 and so on. And that's the measurement record. And what you're trying to do then is to take that measurement record and using this Bayesian inversion, use it to estimate the parameter of your problem. So when you do that, I can make that for many, many things, and then I can just make a picture here of what the probability distribution looks like, slice by slice, as I make more and more measurements. And you can see we start off with a flat prior, but after a while, we obtain more and more information about the interferometer. And we eventually become, pretty sure that it is 45 degrees, this phase. And this is kind of what you've always got to do, and it's always embedded in quantum mechanics in a way, that you make destructive measurements on the output and they give you a result. And if you want to then use that result to infer, so in quantum metrology, you're trying to make a measurement of something, like what is a phase shift in an interferometer, what is the energy level in an atom. You've got to do that inversion. You've got to take the measurement record and ask yourself about what is the parameter that is embedded in the Schrodinger equation that would give you that result. And that is always something that looks like this, combining the results of measurements and then asking yourself what is the probability distribution. So that is Bayesian analysis. And that's part of this whole story. Okay, so, go ahead.
So, is there a way to include phase noise in this model? So do you have a specific time?
Right.
And presumably if you have some phase noise, it should broaden out the distribution again.
The problem with parameter estimation when the system itself has intrinsic noise, that's an enormously studied problem, but it's also more complicated, okay? Like the classic problem is, where you're trying to do image reconstruction, where you're throwing X-rays or something, or photons through at a system, and the system itself has intrinsic noise based on your photo detection uncertainty, or that there's scattering in the system. And then you need to revert to this whole field of maximum likelihood estimation, maximum entropy solutions. And that's part of this problem as well. But I'm not going to talk about that. But I would say it's a well-studied, it's a field of its own. Yeah. Yeah. Down here maybe?
Yeah, this one looks like you did like 30 experiments. So for single experiment, how many measurements do you do? Oh, the question is, how many is your N1 to answer?
This result was done for individual photons. Yeah, this was done for individual photons. You could, in principle, do repeated measurements with many, many photons. But this is done one by one and just combining the results independently.
So, like N1 and 2.
So you can see here, like, let's look at the first one. This guy here, I can tell you for sure that came out of port 1. Because there's zero probability that there's a zero phase shift in the interferometer. Yeah. Right? And if there's zero phase shift in the interferometer, it goes out in the port that it came in, So there must be a phase shift. That immediately tells you that there's a phase shift. It obviously came in, maybe came in port 1 and out port 2, or the other way around. It switched. That tells you that the interferometer is not a perfectly matched interferometer. Because the unitary evolution of a perfectly matched interferometer is 1. It doesn't do anything to it.
Yes. I mean, things with the expression we should call that as P5 and N1 to.
I can give you this notebook if you want. Yeah.
This method of iterating and applying Bayes' theorem again and again for every photon that you detect, would it give the same result as just doing this experiment 30 times and asking probability of this 5 given that 16 photons were detected in port 1?
So the answer is sometimes. It depends on exactly what your system is, exactly how you have to accumulate the results, and whether or not, for example, the central limit theorem applies. And there are classic examples in Bayesian analysis where normal statistics do not work, and we can talk about this later if you want, but they're actually very interesting, they're really classic probability, classic examples in statistics where your sort of naive intuition goes wrong. So this will always work, what I'm showing you here. I think this is as far as I know, this is the optimum way of constructing the knowledge of your probability distribution given that you came into the system with some prior knowledge and you had a certain number of measurement results. It's not always easy to solve a forward problem, which is part of the difficulty, okay? But here it's possible, yeah.
So just following up on an earlier comment, as long as we're doing statistical analysis to get at our parameters, this method of continuously updating with incoming data seems really well suited to a Kalman type filter where you can build in the systematic noise and while you're at it, just get even more information. Why not just do that?
They are related, okay? So all of these things are connected. The basis of Kalman filtering is related to what I'm talking about. I would say the only thing is we have sort of discrete quantum measurements here, which is sort of like, in principle, maybe it's not exactly what we do in the lab, but in principle it's what we could do in the lab. We could run multiple experiments like this. So I agree this is a Gedanken experiment. There are other ways of getting, skinning the cat or whatever, but I don't know if that's an expression here, but this is a perfectly complete description, is all I'll say. It's not the unique. It's not the only way you could present this. Yeah.
Does the scale, the variances scale like quantum with 1 over 9?
Yeah, this scales as 1/1 rooted with statistically independent particles like this. But I'm going to show you just now fancy quantum states, and then we'll depart from that, okay? So that is consistent with what I just showed you. Where I sort of had to employ the central limit theorem, this was a better way. This was a real parameter estimation. And so you can ask the question, can you do better? And the answer is you can. You have to think about this problem differently. This is a problem where I throw photons into both ports, not just one of them. And what I do then is I have my detectors out here and I change the observable. In this case, I can improve upon the standard quantum limit. And what I have to do is I have to call the signal the noise. In other words, I have to look at the difference in photon numbers between detectors 1 and 2, which you might think about as the fluctuations. It's the noise in some way. This is the setup which gives you a better phase resolution. And I'm just going to show you that. you have to input, it turns out you have to engineer an input state which has reduced the base of that as you generate what's called a dual Fock state. You throw in n upon 2 particles into one port, let's call them photons, and n upon 2 photons in the other port. So exactly a known number of photons. This is clearly not a coherent state. This is a Fock state where the number of photons is well defined. The difference in the number of photons here is 0. Okay, so there's no fluctuations in delta E. Then we go through with this input state and use Bayesian analysis. In order to do that, we need to be able to solve the Ford problem, which is what I just told you needs to be always done. Given a phase shift phi, what is the probability of getting delta E? And actually that's pretty straightforward to do. Interferometers look like angular momentum algebra. So basically you have, each photon could be in port 1 or port 2. It's like a 2-level system. It's like a spin 1/2 system where the spin could be up or down. And so there's actually a strong analogy between this system and what you have with an ensemble of spins, which I've been talking about, where you can talk about collective operators that correspond to the addition of angular momentum operators for each one of these photons, if you like, whether they're in port 1 or port 2. They're like spin up or spin down. And in this case, the Jz angular momentum corresponds to the number difference of photons between 1 and 2. And the total J is equal to the number of photons over 2. It's essentially the total number of photons in my system. So this is a very elegant formalism for interferometers, and you can use it to describe the action of the interferometer. Basically, the first beam splitter does a pi upon 2 rotation in this angular momentum space. So you start off at the south pole, and you do a rotation, and then inside the interferometer, there's an evolution which is associated with a path length difference. And then there's a final beam splitter which does another rotation. So I know this is going fast, but it is just the way the theory of interferometry works. Each of the 2 beam splitters is a pi upon 2 rotation. The internal dynamics of them propagating through the paths is related to a rotation about z. And you can construct these using the rotation matrices Jx with a rotation angle of pi upon 2 and Jz with a rotation angle of phi, which is the actual path length difference in the interferometer. So the action of the interferometer is basically a summation of all these terms. You rotate about x, you rotate about z, and you rotate about x. And the resulting angular momentum algebra for that describes the unitary operation of the entire interferometer in a very elegant and concise way. So this turns out when you use the commutation relations between x and z to give you I, phi, j, y. And that is the action of the interferometer. It's a rotation about the y-axis by phi. And you can see that sort of from the picture that I drew above. So we can use Bayes' theorem on this interferometer to calculate what the action is. What is the reconstruction of phi? And the probability distribution for getting delta n given phi is related to the probability distribution that you have an m eigenvalue for the Jz operator. So it's like a magnetic quantity number that tells you about the delta n given phi. And this thing here, which is the Ford problem that we need to solve, what you want then is to take the output of the interferometer and to project it onto the m eigenvalue in modulus squared. It's just the probability in quantum mechanics. To find the output, we just want to use the action of the interferometer on the input state. And the input state is the special state of n upon 2, n upon 2. So when you use this angular momentum algebra, it turns out with a few lines of algebra that you can show that the result of this thing is actually a Bessel function squared, modulus square of a Bessel function of order n with the argument given by the total number of atoms, which is j, and the phase shift of the interferometer. So it's an elegant analytic solution for this problem. And you can go then ahead and you can use Mathematica to tell you about simulations using, this is just a bunch of code here, to simulate multiple measurements of this interferometer. So first of all, I'm going to show you here the Ford problem. What is the probability of getting a number difference in the arms given that the phase shift is phi? If the interferometer phase shift is 0 and you put in equal numbers, the interferometer doesn't do anything. Its identity is its operation. The action of the interferometer is 1. So if you put in n upon 2 and n upon 2, they come out as n upon 2 and n upon 2 in every trial of the experiment. So you never see anything but 0 for the number difference between the 2 output ports. And it's also true for 2 pi. And in between, this number difference grows. And this distribution here, if you cut through, it's the Bessel function. So you can see the wiggles characteristic of a Bessel function. So that's the forward problem, okay? That's an analytic result. That's what happens here. Okay, so now we're in business. We can use an interferometer like this to make a parameter estimation. And let's say that the interferometer is phi equals 0. So you can ask, what is the minimum detectable phase shift in this interferometer? How well can we reconstruct the fact that the phase shift of the interferometer is 0? So once again, I'm not obviously going to show you. I'm just showing you here that this is a simulation of it. And this is an example of a few trials of this experiment. There are actually two results here. This is just accumulating results one after the other for simulations of this experiment. And on this case here, we throw in n upon 2 and n upon 2. And on the right-hand side, we do the same thing where we have paired photons, but we allow the distribution to be distributed according to a Poisson distribution. So it's like a dual coherent state. And when you do this, your knowledge of the phase shift contracts very, very rapidly when you start to accumulate results using Bayes' theorem. And the width of this, the ability to reconstruct the phase shift phi, in this case goes as 1 divided by n and not 1 divided by the square root of n. And this shows you that there are better states in quantum mechanics to use than the coherent states that come from a laser of well above threshold, which you might think is a good thing to do phasing measurements. Okay, so, yeah.
Sorry, this is a Fox or
Dual Fox state input for the phase shift of the interferometer being 0, and you can see with multiple measurements it's reconstructing that phase shift with our probability distribution. So I hope I've touched on a few of the main elements here. I mean, one is that there's a standard quantum limit in interferometry. Another one is that the problem is a Bayesian problem of reconstruction, and this is, this is very general in quantum metrology. And the third one is that by engineering carefully quantum states, such as this dual Fox state, and this is not the only one, you can do better than the standard quantum limit. And in fact, the number phase uncertainty relation that's given by quantum mechanics says that you should be able to get down to 1 upon n. Okay? And this is a problem that gets you to that order. Okay? And there's a whole literature of a whole field of people working on problems that are related to this. So I'm going to stop there if it's okay, and I want to present one more topic, which I think is an important one to discuss. So let's leave this here. Yes, there are more questions on this. Okay, and just briefly here, so I've got like 20 minutes or so. Let me talk about the second subject.
Only a quick question.
Yeah, far away.
What was,
Sorry about this. I think I closed it accidentally. Yep, go ahead.
okay, what have down there is the Fox state, and why do you argue the coherent state is also useful? I mean, will also make the measurements better.
Why do I argue that it would?
The coherent state.
Oh, I see. No, it's just that actually the Fox state is kind of the ideal, and that's because if I constrain the problem, and then I say, I have to make a constraint that the energy that I'm going to send into my interferometer has a limit. Otherwise, I just throw more and more photons at it, and I do better and better. But if I put in a constraint that the energy maximum is this value, the best you can do is to split it into n upon 2 and n upon 2, or other states like that have this dual character. But it's often the case that you produce these photon pairs by a process like parametric amplification that produces photon pairs but has a distribution of them. I know that there's the same number of these arms, but I don't know exactly what number. And that's why we thought about this distribution. That's sometimes important for an actual realization. Okay, so this morning I talked a little bit about the super radiant laser, and I just want to show you an application of that same kind of problem, which we would call quantum synchronization, in this kind of interferometry, this kind of Ramsey spectroscopy. So instead of doing it for a light interferometer like this, I'm now going to talk about the same kind of thing where you have Ramsey fringes, which is like an interferometer that happens in the time domain. And I showed you some pictures that looked at the spectrum of light that came out of a super radiant laser. This is sort of showing what happens if you pump the laser below threshold. With really weak pumping, a super radiant laser has a line. On this scale, it looks like a flat line, but it's actually a Lorentzian that goes out to Texas or something, right? It's a huge, great big Lorentzian there. And then as the system goes above threshold, the thing collapses very, very quickly. And that's because the synchronization occurs as the block vector gets above the equator. And you see the line width narrow enormously, and it comes down to this single atom. So I showed you this before. I showed you that the line width is basically related to the line width of a single atom. And it's a different kind of formula to the normal Shallow-Towns line width that we think about for a normal good cavity laser well above threshold. So what I want to do now is to move on from that topic a little bit and think about whether or not we could employ this kind of synchronization, this kind of collective physics in a spectroscopy, in a metrology system, right? In Ramsey fringes, okay? And I'll explain what I mean by that. So firstly, let's just go through what is a Ramsey sequence. So the idea is that this is probably the workhorse of atomic physics. Basically, you start off with a bunch of systems which you prepare in a well-defined quantum state, usually by optical pumping into a given hyperfine level or quantum state of an atom. And then you apply coherent fields which generate rotations. So in this case here, we've rotated about the y-axis. We've allowed the system to then freely propagate inside the Ramsey sequence. And then finally, we've applied a second rotation, in this case about the x-axis. And finally, in the Ramsey sequence, you make a measurement of the projection of this onto the z-axis, which tells you how many up and how many down have you got, how many in the excited state and how many in the ground state. And that projection of this final block vector, so you've got your two Ramsey zones, one Ramsey zone here, the other Ramsey zone here, and in between, free propagation. The number up and down tells you about, gives you a measure of the fringes in this problem. So this is the expectation value of sigma z, and as I wait longer and longer, make this time in between longer and longer, I can see fringes going between all the atoms up and all the atoms down. So that's kind of Ramsey spectroscopy. I have to have a tuning in the problem because in the rotating frame, I basically am measuring the relative phase accumulation between an atom and a local oscillator, a time standard that sort of goes alongside the Ramsey sequence. And that phase difference is sort of how quickly this vector is processing around the equatorial plane. So it's that frequency that the Ramsey sequence actually measures. So if you can ask the question about what's the limits in quantum metrology of this kind of problem, and so Christian showed you this morning, the relative frequency uncertainty as a proportion of the frequency has a very characteristic form in Ramsey spectroscopy. Basically, well, these are the things that go into it. 1 divided by 2 pi, the square root of the number of atoms or trials, and n, which is the number of cycles. Basically, you want to go as long as you can. And this is even like true of, say, a physics 1 experiment where I want to measure the oscillation of a mass on a spring, on a pendulum, just swinging back and forth. You basically want to measure the first sequence so you know what number you're up to, and then you want to let the thing go as long as you possibly can before you measure where it crosses zero in order to get a good frequency measurement. So it's the same here. You want as many cycles as you possibly can, and then you want to measure very carefully where does this line go across with the biggest slope, and that will allow you to work out what the frequency is of this oscillation. So that's embedded in this. The 1 divided by n is how many cycles, so as many cycles is better. The square root of n is to do with the intrinsic number uncertainty, just what I showed you. You're throwing dice. Every atom decides, am I up or am I down? And so there's intrinsic shock noise in the problem. So the more atoms you have, the smaller that becomes, or the more trials that you do that are statistically independent, they accumulate as the square root of n as well. And so the total number always looks like this. Okay, so why don't you just go forever? And the answer is you can't, because of dissipation and decoherence. So if we add spontaneous emission into my atom, maybe while it's going around the equator, it's got some likelihood of being an excited state, and maybe it spits out a photon. So real Ramsey fringes are going to look like this, with an envelope which decays exponentially, which is based on the decoherence rate. There's a balance. You basically want as many cycles as you possibly can, but if you go too long, the fringes have just about disappeared, and the gradient is so small that you can't tell when it goes through zero. And so there's a balance, which you heard this morning, the same idea. It turns out that the best you can do by, just finding the derivative of this function and see where's the maximum and just calculate what is the ultimate you can do for delta f upon n. It's the 1 upon e time of this distribution. So basically you want to go out to a time which is 1 divided by the gamma of this envelope. And then you want to stop, because you're no longer winning the 1 upon t. Eventually you just get 1 upon root t, where you take this and you combine many different experiments, starting again and again and again and again and again. That's your best strategy. If you go longer in any given one experiment, you'll do worse. Okay? The optimum strategy is to go to 1 upon n time, and then reset your experiment and do it again and again and again. So that is a fundamental idea of Ramsey fringes. And actually, often, it's not the spontaneous emission rate that limits you, it's other technical noise. There can be all sorts of other dephasing in the problem. So often the envelope actually isn't just determined by the spontaneous emission rate, but by other things in the problem, which we call T2. Because we almost define that to be the envelope of this function, okay? And that, going to the 1 upon e time of this is what you need to do, okay? So, sort of clear, questions? Confused? Okay, what's this got to do with what I'm talking about? This is general Ramsey spectroscopy, but I now want to throw a wrinkle on this and show you a system that doesn't look like any Ramsey experiment, which I think, at least I had ever thought about. Okay, this is the idea of using collective physics. So this is an active Ramsey sequence, where I'm actually pumping the system. So I'm going to put the atoms in a pad cavity, like I did in the super radiant laser. I'm going to allow them to dissipate energy out the cavity. The gamma C, this is the cooperativity times the single atom alignment. This is the emission rate of an atom through the cavity rather than into free space. It's the same thing that determines the alignment of the laser. And we're going to incoherently repump the atoms during the Ramsey sequence, okay? So we're going to keep on replenishing the population in the excited states so that we can generate population inversion and so that we can get the atoms to synchronize. So this is our system. Atoms in a cavity like this. We're going to generate population inversion. So in order to get incoherent pumping between G to E, you shine a laser onto some auxiliary state and then it relaxes. And if this relaxation rate is very large, you can generate population inversion. This is why lasers have to have at least 3 levels, if not 4 levels. So it seems like a bad idea. Surely I'm adding noise. I'm repumping the system with random dice. I'm throwing dice, deciding randomly where the atom's going to the excited state. This doesn't sound very good for quantum metrology. There's vacuum noise from the output coupling. Photons randomly decide to go out. All this noise sounds bad. Surely this should make your Ramsey sequence not so good. Well, that's not true. So the basic idea is that you've prepared a bunch of atoms with your Ramsey pulse in a given direction, and then these atoms are going to synchronize and rephase. That's part of the problem that I talked about this morning. So let's say an atom gets a bad glancing collision and dephases with the rest of the population. In normal Ramsey spectroscopy, that atom's done for. It never contributes again to the signal. But here, there could be a torque on its block vector which brings it back into alignment with all the rest, and that allows the fringe to carry on, right? So you could have continuous rephasing of the atoms in a different kind of Ramsey spectroscopy where each atom isn't working individually but knows about all the rest and is continually synchronizing with the rest of the ensemble. So this is a simulation. It's an exact calculation using the SG4 theory I talked about. The gamma C is so C is 1/5. So gamma C is 1/5 of the natural length of the atom, which is the same as the 1 upon T2 time. And we're pumping the system in the optimum region where the block vector is 45 degrees above the equator. And the end result is shown here. You can see that the Ramsey fringe decays much slower. It's this solid line here. And for reference, I showed you what would happen if you just used the normal Ramsey sequence with that gamma, which is much slower. And actually, this green line here corresponds to just a fit with an exponential decay, where the envelope is given by the line width of the super radiant laser, which is gamma C. So I told you that it was an extremely narrow line width laser. So the same narrow line is giving a very long time for this system operated in the Ramsey fringe sequence. So it's kind of interesting. We've used collective behavior of multiple atoms in the ensemble to push out the time to which we can do the metrology for. And that allows us to make a better precision measurement. So what this shows is the envelope. So it's e to the minus lambda t. So lambda is the decay rate of the envelope of those fringes. And I'm showing them to you for many atoms, from 0 to 250 atoms. So you can sort of see that if you don't have very many atoms, this system actually works not very well at all. The envelope decays very rapidly. This is the single atom result. So this is your benchmark for conventional Ramsey spectroscopy. This is the line width of the super radiant laser. And you can see that providing you get enough atoms, maybe like 50 on this plot, you start to win. And by the time you get down to hundreds of atoms, this collective behavior is causing the decay rate of the fringes to be pushed way, way out. Okay? And eventually you end up with the collective line width determining the Ramsey spectroscopy. So this shows you what happens as you, to this envelope, as you change the number of the pumping rate for 200 atoms. So when we don't pump hard enough, the block vector stays down at the south pole and the synchronization is not there. As we start to pump harder, we start to force the block vector up into the northern hemisphere, and the laser goes above threshold, and this is exactly where the Ramsey sequence also starts to get its optimum quantum metrology value. And then eventually we pump too hard and the synchronization starts to go away. The optimum is somewhere just above threshold, where you're adding noise but no more noise than you have to in order to get the atoms to synchronize together. Okay, so this is kind of the key slide here. Let's see how we're doing. Okay, we're just finishing here. This is probably the most important slide in this part of the talk here. There's a subtlety, or subtlety about what is really going on here in these pictures that I showed you. And in particular, what is the difference between an ensemble average, which is the accumulated results of many experiments, and what happens in a single trial, a single run of the experiment. So I'm going to walk you through that. So this shows you what's really happening. And this is like what Klaus talked about in terms of homodyne measurements and a single measurement record. Okay? And so this is a simulation done in that spirit. We have our system with our Ramsey sequence sitting here. And we're taking the signal out and we're going to make a measurement by interfering that with a local oscillator in the reservoir. So doing this, we obtain phase information about the field that's coming out. So what actually happens? What does the conditional measurement look like? Well, this is, red line is a single run of the experiment. So it's not decaying actually. It goes down here and it goes up and it goes down and it goes up. What's happening here is that the atoms are always rephasing, so the visibility of the fringes is always of order unity. And if I sit out there in the outside world, I can tell you what the fringe phase is by looking at the phase of the light which is emitted. So as that phase changes, I know exactly what it is. The fringe visibility is always of order unity. And these fringes will persist forever, you know. This plot I can make again, going out to Texas or whatever's in that direction, I know. But they go on forever, okay? They never decay. Atoms which spontaneously emit get repumped. Atoms which dephase, they rephase, okay? The fringes go on forever. But what does happen, and why did I show you that decaying with gamma C thing? The answer is that if I was to do many runs of this experiment, what I would see is that initially these red lines all were in sync, in lockstep with each other. But that over time, the positions of the maxima and minima of these fringes would start to diffuse. That diffusion is the back action of the measurement. I'm making a measurement in the reservoir, and that measurement result has a back action on the system, and that system causes the phase to undergo a diffusion. And you can sort of see that if you just run many experiments and just ask, where is the first crossing, zero crossing? Where is the second crossing? Where is the third crossing? Where is the fourth crossing? These are histograms of many of these trajectories showing where those crossings are. And you can see that over time, the crossings are starting to diffuse out with a Gaussian behavior. This is like a random walk, like an Einstein diffusion process, just like I told you about with the quantum line with the laser diffusing around 2 pi. This is a very similar thing where the fringes are diffusing, slowly diffusing. And you can ask, like, what is the diffusion rate of these fringes? And the answer is, it's this gamma C thing, which determines the line width of the laser. So that is what is really going on. the fringes always have unit visibility, but my ability to determine the frequency of my system slowly degrades over time because the fringes are slowly diffusing due to the back action of quantum noise. And that affects my ability to make a parameter estimation. Okay? So that doesn't mean that we don't win. We do win. So my argument that we gain by this factor of the cooperativity is true. So what you want in order to make an ideal quantum metrology experiment like this is to have a cooperativity which is small, because C gamma should be very small, allowing T to be very, very large. So I put a small number down here, 0.01, 10 to the minus 2. I can go out 100 times longer in a Ramsey sequence. Why do you make C 0? The answer is that you need to be above threshold, and that means that N times C, the number of atoms times C, has to be much bigger than 1. So if C's 10 to the minus 2, I need to have 10,000 atoms in my system to make NC 100 in order to get above threshold. But that's a great result. You can get a cooperativity which is small and compensate for it by having many, many atoms which are collectively talking to each other, and you can push out the quantum metrology time. So this is a theory proposal. This has never been done experimentally, but I think it's an important aspect because most of our quantum metrology systems, especially our conventional Ramsey spectroscopy, is a single atom phenomenon. We may have an ensemble of atoms, but they're all acting as individual atoms and not necessarily talking to each other. But this shows you the power that you could get by going beyond that. Okay, well, I think that's really all I wanted to show you. I don't know if there are questions. Otherwise, I'm going to finish at this point. So thank you.
They asked me to be him because he's not the president. I will stand here and ask other questions.
Yeah.
Yes, please.
What's the minimum number of parts that you can detect in the experiment?
The minimum number of particles you can detect in this.
For example, can we do this so we can actually keep it?
So the answer is absolutely. So it depends on the system here. If I put a single atom in a cavity, you can see that atom. Okay, you might have to work hard. Okay, so the typical experiments that I'm talking about here have between 10,000 and 100,000 atoms in a cavity. Okay? That's not to say that you couldn't do this with 10 or 100 or even 1, but it would be a different kind of experiment. You have to work hard to do it. But you could see this in any system where you have spin 1/2 systems coupled by a dissipative boson channel. So superconducting qubits would be a classic example that I could do it. A bunch of coupled optomechanical oscillators would be another one that I could do. We've thought about doing this with the ion trap down in NIST, with John Bollinger's experiment, where there's many of these beryllium ions, which are spin 1/2 systems coupled together by phonons. And then you could do this with N as 100. So the answer is absolutely system dependent. The physics is always going to be the same, but where you lie depends on what field you're working in. So I think this was proposed really for doing ultimate precise spectroscopy with the atom cavity QED systems. And I think you should think about anything up to 100,000 atoms there.
More questions? It's going to be the last questions for Mario because this was the last presentation.
So I convince you all.
It was also wonderful. Good, let's thank Mario again.